we're going to look at state space model. Okay, how can we build and how can we analyze data that comes naturally sequentially, so over time? Okay, this module is going to be split into two parts. First, what we're going to cover here in this video is the theory behind state space model. In the second part, in the following video, what we're going to see is how can we build linear model in order to analyze these time series. Okay, the first part is the core theory, then is how can we build model to adapt to different situations. So the references for the first model are going to be the chapter 12 from the book for the class and chapter 18 from Machine Learning and Probabilistic Perspective from Murphy. So time series, how does it look like? Okay, what we have is data that is collected sequentially over time. So how do we analyze, how do we interpret data that is time dependent? Okay, this is what we're going to look at. Here we have an example. We have on the horizontal axis time, where we have the first digits are the years, the second one are the months. Okay, so this is from January 2017 till December 2017, 1 year worth of data. And what you see on the vertical axis, it could be, for instance, the temperature recorded on this period. What you see here, the red line would be the expected value, and the green confidence region around the red line would be the plus and minus 1 standard deviation associated with that quantity. So here we have intrinsically noisy data, okay? So what do we want to do? What are the possible tasks with this time series? It could be first to filter the observation noise, to remove that variability that is associated with the observation process, and to remove it from the raw data. To infer what would be the line here with a cyan color that would represent the expected value for the underlying process for our time series. A second task would be to forecast future observations. From what I've learned about the kinematics of that temporal process, what I want to do is to forecast what's coming next, okay? Given what I've learned here, how can I forecast what's gonna come for the months, for the years to come, okay? Then, related to filtering the observation noise, how can we estimate the hidden states? So hidden states, we're gonna see that in more details, are gonna be the variable that are not directly observed here in the process. So here we have first hidden state, which could be the baseline behavior. So the underlying behavior associated with the temperature over time that is not associated with the observation noise, but also that could be inferring what is the speed, so the rate of change of the underlying process. So for instance, here I know that my rate of change is 0. My rate of change here has some quantity. I want to learn this online in real time as data come in. So this is what we say when we say estimate hidden state variables. And finally, what we want to do is detect anomalies. So you see that visually you can really identify that somewhere around here, so we can look at the raw data here, somewhere around here we have a change in the regime for our underlying process. Okay, so when you have a lot of data, it's in hindsight, it's fairly easy to recognize this. But how can we do this in real time online as data come in? To identify that here, oh yeah, there's something going on. I have a different regime. I need to switch regime. So try to detect anomalies like this. So changes in regime. So here what we have on the graph is the probability of both regime. First regime that is a constant speed and the other one which has a trend. Okay, so as first regime has a 0 speed and the other one would be a trend, so a constant speed regime. So we said that initially the one with the trend has a 0 probability when at some point we have some shift, okay? How can we learn to do this in real time as we're collecting data? Okay, so an overview for the methodology. So in terms of the field of machine learning, what we're gonna see here is often referred to as state space model. If we look in the field of control theory, what is used to control aircraft or control like rockets, this is what we refer to as Kalman filtering. And in the field of statistics, we typically refer to the theory we're going to see here as dynamic linear model. Okay, even if we can have different names to talk about the concept we're going to see here, they're all building on the same underlying math. Okay, and this is what we're going to see together. And all these things, all these concepts are building on Gaussian conditionals. Okay, the same Gaussian conditional we saw since the beginning of the class. And here we're going to review this concept to be sure that everyone starts with the same solid foundations. Okay, we're going to walk through this specific example together. So the origin of this field comes from the Kalman filter. Okay, this is an algorithm that was developed for the NASA as a guiding system for the Apollo mission in the 1960s. So, and this has not become obsolete, as it is still what's used today in modern rockets. This is really a powerful tool that can be used in order to analyze time series data. Okay, so we can see this as what we're going to see today. It's a kind of rocket science applied to civil engineering. Okay, we're going to break that down and see how can we use it and how can it be useful for our cases where we have time series. So overall, what we're going to do, we're going to make a revision of the key concepts about the Gaussian distribution, okay, Gaussian random variable, okay, because everything we're going to do here is going to be relying on the theory associated with linear model of Gaussian random variable, and how can we first propagate uncertainty through linear function of random variable, and also have analytical formulation for Gaussian conditional, okay, how can we do explicitly and analytically tractable Bayesian inference in the case where our joint knowledge is described by a multivariate Gaussian distribution. Okay, we're gonna review these concepts so that it's fresh in your mind so that we can build on this. Then we're gonna look into the theory associated with state space model. Okay, all the theory, all the mechanics that leads us into building the fundamental equation. And then we're gonna see, okay, what can we do with these equations? We can do three main tasks. The first one is estimating the hidden states associated with a stochastic time-dependent process. The second one is forecasting in the future what's going on. And a third task is smoothing. So going back in time and see, okay, given the data I've seen 2 years ago, how all the knowledge I've seen so far can improve me going back and seeing what actually happened in the past, okay? So estimation, forecasting, and smoothing. These are the three things we're gonna look at together here. Another thing is that we're gonna see that even if we do time series analysis with the Kalman filter, we still have parameters, okay? And these parameters need to be estimated from data. So we're going to see how to express these parameters and how can we learn these parameters, either through a Bayesian approach or to a maximum likelihood approach. Finally, we're going to look at the theory behind the regime switching, so detection of anomaly. So how can we have multiple regimes competing together and to detect the possible change point from one regime to another. And finally, we're going to look at what are the limitations, what are the potential pitfalls that you need to look at carefully in order to safely apply the theory we're going to look at today. So we're in the module 7 here, state space model for time series analysis. Okay, so first section, we're going to review the key concept associated with the multivariate Gaussian or multivariate normal distribution. Okay, so the first key thing is, what are the properties associated with function of Gaussian random variable? And here we're going to specifically look at linear function of Gaussian random variable. Then we're going to look at how can we generalize this through the transformation rule or the change of variable rules. And finally, we're going to look at the second property that is key for us. How can we look at conditional Gaussian PDF? Okay, how can we do analytically tractable Bayesian inference for jointly Gaussian random variables? Okay, so first let's look at function of Gaussian random variable. So G here is a deterministic function, and here X is a vector of random variable. So even if J is a deterministic function, since it takes as input X, which is a vector of n random variable, the output of G is still going to be a random variable, okay? So in this case, in this context, we assume that we know the joint PDF for X, okay? And what we're going to be looking at is what is the joint PDF for G of X, okay? My deterministic function of my random input. So we're trying to characterize what is going to be the PDF of y, which is the output of my function g of x. Okay, so here I can have here n input to my function, and that function can have m output. Okay, so it's equivalent to say that actually I can break down this function into n function that each take as input my random variable. Okay, my random vector x. So the question, as I mentioned earlier, would be to how can we characterize the joint PDF for y? Okay, so there are two cases we're going to see here. First case is a one-to-one transformation, which is one input variable x, one output y. Then we're going to generalize this. What happens if we have many n and many m? So an arbitrary number of input random variable and an arbitrary number of output random variable. Okay, and here we're going to restrict ourselves to a special class of function, linear function. It means that here we're only going to consider g of x that are in the form ax plus b, where here a is a deterministic matrix, x is a vector of random variable, and b is a deterministic vector. Okay, so we have this linear form in our function because we have special property, as we've already seen, linear function of Gaussian random variable. The output is still Gaussian. So remember what we saw earlier. So for the first case where we have one input, one output. Okay, I have only one x and I have only one y. So in this case, we can use this relation to say that f of y dy equals f of x dx. Okay, it means that we need to conserve, we need to keep the probability constant in the x space and in the y space. So here I have my PDF for f of x. Okay, the horizontal axis is x, the vertical axis is the PDF f of x. So here I can say that if I have a little sliver dx, and this is my function, so this is my space x, this is my space y, so this is my function, y equals ax plus b, where a and b are deterministic constant. This would be my PDF for y, so that the probability content on the sliver dx must remain the same probability content on my sliver dy, okay? And there's a change in the size of my neighborhood from dx to dy. And this change in the size of neighborhood is controlled here by my function. So here, if I want to obtain my PDF f of y, I simply send my dy on the other side of the equality, and I take the absolute value. Why? Because the PDF must always remain strictly positive. Okay, so if I want to enforce this, I need to make sure that here I use absolute value in case this derivative would be negative. Okay, so this is simply the inverse of the derivative of dy dx, dx dy. So for a linear function, y equals ax plus b, where x is a random variable, it implies that y is going to be a random variable as well. So in that case, dy dx is simply equals to a. Okay, dy dx is simply the slope of my function here. So in absolute value. So in this case, if dy dx is in absolute value a, dx dy is 1 over a. So in that case, the result, if we apply this function to the case where x is normal with expected value mu x invariant sigma x squared, then it means that y is still normal with expected value. So I evaluate my function here, but I replace x by the expected value. So a mu x plus b, and the variance is going to be a times the standard deviation square for the variance. So the standard deviation is going to be multiplied by my function a. Okay, so my variance is going to be a sigma x squared. Okay, if we look at this with the numerical example, what we have here is our PDF for x, where x has an expected value of 10 and a variance of 25, so a standard deviation of 5. So what we can see here, the expected value is 10, and what you can see here is the mean plus and minus 1 standard deviation. This is what you see in the dashed dot pink lines. This is expected value plus or minus 1 standard deviation. So what you see is if we project both the expected value and the plus and minus 1 standard deviation interval over our function and reflect that back on this other axis, which represents y, the output of that linear function, we can see that we can directly obtain the expected value and the plus and minus 1 standard deviation for the confidence interval of our PDF for y. Okay, this is exactly it. So here, since my slope is y equal to x, the expected value is going to be 2 mu x, and the standard deviation is going to be 2 sigma x. Okay, this is exactly what we have visually here. Okay, this was for the one-to-one transformation. For now, the general case, so in this case, we're going to look at two input to two output transformation. So I have two input x's, I have two output y's, okay? And I want for each x1, x2, there's a unique one-to-one transformation, g of x, that leads to a y1, y2. So in that case, I want to know how my neighborhood probability or my neighborhood change from x to y, because I need to maintain the same probability content on these two neighborhood, these two sliver of probability space. So here what I can say, I can use the same relation, but now in a multivariate domain to say my joint PDF for x times dx, where dx here, which is representing the space I have in my two-dimensional domain, is equal to the PDF of y dy, the same corresponding space, but this time in the y domain. So again, I have the same goal. I want to express what is f of y, okay? My joint PDF for the output of my linear function. I do this by doing f of x dx divided by dy. Here I miss, I should have the absolute value here to make sure I maintain my probability content. So here I can obtain this, or I need to define our first concept, is going to be the Jacobian. Okay, the Jacobian is going to be the partial derivative. In this case, the derivative of yk, so my kth output y, with respect to the ith input variable. Okay, this is what we have here. So dyk dxi is represented by this Jacobian ykxi, or I can simply use the indexes jki. Okay, the kth output for the ith input. So this is what defines my Jacobian. Okay, the output, the derivative of the output with respect to the input. And this Jacobian is used to calculate what is the size of the neighborhood to go from this my y space to my x space. So in this case, I have my Jacobian which contain all these terms. So all these partial derivative. Okay, so the first line is going to be the partial derivative of the first output with respect to all the input, from the first input to the nth input, the last one. And each line represents a different output for my function. So at the end, we can see that each line is that in that Jacobian is the gradient vector of my first output, second output, and up to my nth output. Okay, and here my dx dy, which is the inverse of my derivative for my transformation function, is going to be the determinant of that Jacobian. Keep in mind, the determinant represents how much that determinant matrix is going to warp my space. Okay, how much change in my neighborhood size does this partial derivative function or partial derivative matrix will create in my linear function. So my change in neighborhood here is measured by the inverse of the absolute value of the determinant of that Jacobian matrix. And dy dx is going to be simply the inverse of this, so the determinant of gy gx. Okay, so at the end, what we're looking for here, we said it's going to be f of y, my joint PDF for y, the output of my function, is going to be my joint PDF for my input times the inverse of the absolute value of the determinant of my Jacobian for my partial derivative for the output with respect to the input. Okay, so let's look at the special case where we have an arbitrary number of input, arbitrary number of output, and we have that linear function ax plus b, where x is a random vector, a is a deterministic matrix, and b is a deterministic vector. So here I have my vector of random variable from x1 to xn. I have my expected value from mu1 to mun. I have my covariance matrix that is associated with my random vector. So keep in mind, my diagonal contain all the variance terms for each marginal PDF, and the diagonal terms contain all the covariance matrix. So the covariance matrix, keep in mind, it's always the correlation coefficient between a pair of random variable times their respective standard deviations. And this matrix is, keep in mind, symmetric. Okay, always the same terms on the upper and lower diagonal terms. Okay, so now if we break down our linear equation, we say that y, the output, is going to be a vector that contains m random variable is equal to my matrix A, it's a m by n matrix, times a vector n by 1. So keep in mind from the size, I can multiply here n by n, it works, plus a vector of m by 1. Okay, so the product of this is going to be m by 1 vector plus a vector of m by 1. This is my b that I have here. So x is a random vector, y is a random vector. And here my matrix A corresponds exactly to what I defined earlier as my Jacobian. Okay, so I can obtain, in the case of linear model of random variable, an analytical formulation to propagate through these linear functions the uncertainty about my input variable. So in this case, the expected value for y is a mu x plus b. The covariance for y is a covariance for x, a transpose. My cross covariance, so the covariance between the x vector and the y vector, is going to be obtained by doing a times sigma x. Okay, that represents the dependency or the covariance between x vector and y vector. So at the end, I can represent my entire joint knowledge for both x and y by my concatenating together my expected value, so my expected vectors, and my covariance matrix. So here I have sigma x, my covariance for my input, sigma y, my covariance for my output, and my cross covariance here, where sigma x, y, and sigma y, x are simply the transpose of each other. Okay, second key property on which we're going to build in this module is the Gaussian conditional PDF. Okay, so we already seen that the conditional distribution of multivariate Gaussian are still Gaussian. Okay, that's going to mean we're going to be able to do analytical Bayesian inference in an analytically tractable way. Okay, so here let's consider x to be parted into two sub-vectors. So x is a general vector which is going to be parted into x1 and x2. So we're also going to split the expected value into mu1 and mu2, each being two vectors. And my covariance matrix is going to be split in sigma 1, so the covariance for x1, sigma 2, the covariance for x2, and sigma 1, 2, my cross covariance between the vector x1 and the vector x2. Then what I can do here is, let's assume that I observe the vector x2, but not the vector x1. How does my observation for x2 change my knowledge for x1? Okay, this is what Gaussian conditional allow us to do. So in this case, I'm gonna try to obtain the formulation for my conditional PDF of x1 given x2. Okay, how am I going to do this? By dividing my joint PDF for x1 and x2 divided by x2. Okay, in this case, if we do that exercise, we're going to obtain a normal PDF form. Okay, that joint normal PDF form is going to be defined for x1. What is on the left of my condition here is going to be defined by an expected vector and covariance. And these two quantities are defined by these two formulations. Okay, we have an analytically tractable way of doing that Bayesian inference, where all the terms in the conditional expected value or conditional expected vector and conditional covariance are a function of all the quantity we have defined here. So either mu1, sigma 1, 2, sigma 2, mu2, or what we have here is x2, where x2 is going to be the actual observation for x2, okay? The actual value that we're observing. So this is for the general case for an arbitrary number of x1 and x2. However, if we simplify it to the one or two-dimensional case where we have a single variable x1 and a single variable x2, in that case, these long equations simplify to this simple case. Function of mu1, rho, my correlation coefficient between x1 and x2, and sigma 1, my standard deviation for x1, mu2, mean for x2, sigma 2, standard deviation for x2. And x2 is actual observed value for my second random variable. And finally, my sigma 1, 2, which does not depend on x2, it's independent of it, is sigma 1 square root of 1 minus rho square, where rho is again my correlation coefficient between my two random variables. So let's see once again the example we saw about how can we update our knowledge about two adjacent beams. So here we have a span which is made of several beams, and we know that these beams are made in the same factory using the same process by the same people. So in that case, we have some prior knowledge about the true resistance of the two beams. Okay, these two beams are side by side, made by the same people in the same factory, so I know that they have the same prior knowledge. So both have a prior expected value of 500 kilonewton meters, and they have a standard deviation of 150 kilonewton meters. Okay, perfect. So given that they share many processes associated with their fabrication, we know that their strength is going to be correlated. Okay, so if I assume that the correlation coefficient is 0.8, so the rho 1, 2 is 0.8, and I observe that the strength of the second beam is 700 kilonewton meter, how does this change my knowledge of the resistance for the random variable x1? Okay, we're going to explore this through Gaussian conditionals. Okay, we're going to express that Gaussian conditional. How does observing x2 modify my prior knowledge for x1? Prior knowledge is expressed here. And this is going to be through the conditional expected value and conditional variance. So it's going to be described by a normal defined for x1 with expected value 660 and standard deviation 90. So keep in mind, my prior knowledge was that the expected value was 500 and the standard deviation was 150. After observing that my second beam is 700, now it changed to an expected value of 660 and standard deviation of 90. So if we look at the detailed calculation, my joint knowledge for x1 and x2 is described by my expected vector and covariance, which I can build from the prior knowledge we defined in the previous slide. So expected vector and covariance matrix, okay? Where we have here the variance, so the standard deviation square for each variable. Here is going to be the correlation coefficient that we define as 0.8 times 150 times 150, the prior standard deviation for each resistance of each respective beam. Then if I define my conditional PDF by the joint divided by the marginal, I obtain that conditional formulation for which the expected vector and standard deviation are given by these formulation. If I just fill in the number, so this is mu1 500 correlation coefficient times prior standard deviation, my observed value 700 kilonewton meters minus 500 kilonewton meters, which is my mean for mu2, divided by prior standard deviation, the result 660 kilonewton meter. My posterior knowledge for my first beam, given that I've observed that my first one has a strength of 700. Same thing for my variance. My prior variance was 150 kilonewton meters. My posterior variance shrank to 90. So by observing the strength of the second one, it reduces my uncertainty for the strength of the first one. So this is what we can do. This is how we can use this. And if we want to look at visually what's going on here, we can see that what we did here is that we modeled the joint for x1 and x2. Our joint knowledge for the resistance of our two adjacent beams. This is what we present here in that joint PDF. This axis represents the strength or the resistance of the beam from 0 to 1,000 kilonewton meters. This is the same thing what we have for the second beam X2. And this surface represents that joint PDF, where we see that that bell curve is squashed by the positive 0.8 correlation. Okay, we have a positive correlation here. If the strength of one beam is high, the strength of the other beam is high as well. And what we can see here in the pink line is like we've taken a slice in that joint PDF. Oh, before looking at that slice, what we have here as the red line would be the marginal PDF. Marginal PDF for X1, marginal PDF for X2. Okay, the respective univariate PDF. What I've taken here in the magenta or the pink line is a slice in my joint PDF. That slice is not taken in everywhere. It's taken at the coordinate x2 equals 700 because this was my observation for my variable x2. So I take that slide, but here what we have to see is that the joint PDF for x1 and x2, what we have here, that curve, if we integrate over the entire x1 and the entire x2, the result of that integral is 1, okay? So if I take a slide in that joint PDF, if I take a slice in my joint PDF, that pink slice, it won't integrate to 1. The whole surface integrate to 1, that slide doesn't, okay? In order for the slide to integrate to 1, I need to divide by the marginal PDF of x2. So this is the marginal PDF of x2. So evaluate at x2, where x2 is my actual observation. So I take that curve here, divided by the height of my marginal PDF, at the same value. And if I do this for all possible value of x2, I would have a graph that would look like this, which look like a ridge, okay? Because here what you have to see is that the expected value is function of the actual observation. The standard deviation is not. So the end result was going to be a ridge. Here that's going to be the same, only the expected value change over that ridge. The width of the ridge doesn't change as a function of x2. Where here, the pink slide represent the actual normalized PDF, okay? For where the expected value of that PDF is going to be 660, the standard deviation of that PDF is going to be 90, okay? This is visually what's going on with this Gaussian conditional equation. Okay, so in summary for this theory, for the multivariate Gaussian, if we have linear function, so A is a deterministic matrix, B is a deterministic vector, so Y equals AX plus B, where X is multivariate normal or Gaussian. Keep in mind, normal and Gaussian are taking as synonym here. Y is still going to be a random variable. And here we can analytically express what is going to be its expected value, variance, covariance, etc. So the expected vector for Y is A mu X plus B. The covariance is going to be A sigma X A transpose. And the cross covariance between my X vector and Y vector is sigma X times A transpose. And then if I want to build my joint knowledge for X and Y, I can. So here I'm just going to concatenate together my expected vectors and going to concatenate my covariance and cross covariance matrix, where keep in mind, sigma xy is the transpose of sigma yx. So once I got this one, I want to obtain the other one just by transposing it, because of the symmetry property of that covariance matrix. Then the second key property that we're going to reuse here for time series is that we can directly do an ultimately tractable Bayesian inference. Okay, so I can express the joint posterior knowledge for X given that I have observed Y. Okay, so my joint PDF for X and Y can be expressed through the equation I will have obtained before, and by dividing by the marginal, I obtain this closed form solution, where that conditional knowledge, depending on what value Y I have observed, is expressed by this conditional expected value and conditional covariance, which have these closed form solutions. Okay, so these are the key fundamental blocks that we're going to reuse in order to create models for time series. Okay, so let's put that time series analysis into a kind of toy example context. So let's consider here that we have a cannon man, okay? That person is going to be shooting the air. So given an initial position, an initial exit velocity from the cannon, and a known acceleration, we want to predict over time what is going to be the position, the speed, and the acceleration of that person over time. So we can do this from the fundamental kinematic equation that we've already seen. So we can say, for instance, if we use S to describe the position of that Kalman man, so we can say that the position at time t plus 1 after it was shot is going to be equal to st, the current position, plus s dot. So the dot here represent the first derivative with respect to time. So in this case, it would represent the speed. So the speed time delta t. So what is the change in time between t and t plus 1? Plus 1/2 times s double dot, so the acceleration of my Kalman man, times delta t square, where it's the time between t and t plus 1 to the power 2, plus w, where w is an error, okay? Because this projectile is subject to the environment. It could be air friction, it could be perturbation, anything that could happen here. So this model is not perfect. W is there to account for the fact that this model is not exactly the reality. So this is the kinematic equation, only to predict the position over time. But then we have additional knowledge. For instance, how do we predict what is going to be our speed over time? So to predict the speed over time, we also have a kinematic equation to do this. I know that my speed at time t plus 1 is going to be my current speed st plus the acceleration time delta t plus w dot. Because my model is also not perfect for predicting ahead what's going to be the speed. So I need to take into account that my model is imperfect. And I do this by having here a model error. And I have a third component I need to include in my model. How is going to acceleration change over time? And to do this, I need to account for a third variable, st plus 1. Okay, in this case, st plus 1 is going to be equal to st. So the acceleration, we assume it's constant over time, plus w double dot, where w double dot is going to be my error associated with the acceleration. The fact that this constant acceleration model might not exactly capture the reality of my physical phenomenon, okay? So in terms of state space model, we're going to consider here that these quantities are going to be hidden states that are not directly observed, okay? We're going to see why. So here, we're going to say, what is our initial condition at time t equals 0? So at time t equals 0, we have our initial state as 0. So the initial state as 0 include the knowledge about the initial position, the initial velocity, and the initial acceleration, okay? This is going to be a vector. Then what we can do is, using the kinematic equation we've seen here, I can predict ahead, given my initial position, speed, and acceleration, and this kinematic equation, I can predict where I should be at time 1 after a time step delta of length delta t. But here keep in mind that even if I would know perfectly my initial condition, because my model is not a perfect representation of reality, I won't know exactly where I'm at time t equal 1, okay? There's going to be uncertainty associated with that forecast because of my process error here. So then what I want to do, I want to make observation in order to correct my quantity I have predicted, okay? But here, the thing is that my y, my observation, is not exactly the reality. Because in practice, it's really common that my device I'm going to use to observe some quantities are going to return imperfect observation. There are going to be some noise or some errors added on the actual quantity I'm trying to observe. This is intrinsic with almost any observation process. So this is why we call S dot, and S double dot hidden states, okay? Because I don't exactly observe S. I don't exactly observe S dot. I don't exactly observe S double dot, okay? Neither the position, neither the speed, neither the acceleration. What I am actually observing is Y, which is, in this case, the actual position plus an error term. The error term associated with my observation process. So here the observation is Y. My hidden states would be the position, the speed, and the acceleration, okay? So here, as I said, I initially predicted ahead, given my prior knowledge, what could be the state. That prediction was imperfect. Now I'm saying, okay, I'm actually observing the position, and I want to combine the prior knowledge from the prediction I made, as well as the knowledge coming from the observation, and I want to combine these two pieces of information to have my best possible information about not only the position, but the position, the speed, and acceleration. So I want to use my actual observation y1 in order to update my current knowledge about s dot, and s double dot. Then what I do, I use that posterior knowledge to go forward. I use that posterior knowledge at time t equal 1 to predict at time t equal 2 using my kinematics equation. Then I'm going to observe, update, predict, observe, update, predict, observe, update. And I go like this recursively over time, over and over again. And the strength and the key aspect of that process is that it can be done online as data comes in. Okay, so we're going to look in more detail. Now we saw this conceptually. How can we put like mathematics on these concepts so that we can start analyzing data? Okay, so we're going to look at the first conceptual introduction. This is a little more technical than what we've seen here. Then we're going to look at what is the basic problem setup to build time series model. We're going to look at what is the special notation we need to introduce in order to really build on the concept we're seeing here and to develop the full equation in a tractable, with a tractable mathematical notation. And then we're going to look at the two key steps we just saw. How do we predict ahead and how do we update using our actual observations? And then we're going to put that into application into a temperature monitoring example. And then we're going to see how all of this generalize into the Kalman filtering equations. Okay, so the first contextual example we're going to look at is going to be bare simple. Okay, we're going to say, imagine we're trying to estimate over time what is the actual temperature in a room over time. So let's imagine that what you're seeing here in that graph, the horizontal axis is time, let's say in hours, from now until 5 hours in the future. The vertical axis is the state. In that case, could be the temperature in the room. So what you see here, the little points you see here are the temperature at each hours. And this, let's assume, are the true value. So we see that over time, temperature is roughly constant, but it's not exactly constant. We have some small fluctuation over time, okay? So this is the most basic time series problem setup. But the issue here is that we don't exactly have access to these quantities. These are the true state, but we don't have access to these true states. Okay, what we have access to are imperfect observations. Okay, the pink squares or the pink diamonds you see here are my YT, my inexact observation. So what I want to do is to retrieve the blue line you see here from the pink dot you can see here. Okay, so what we're going to be able to do when we build our time series analysis model using state space model is to retrieve what is presented here by the red line as well as the red confidence region. Okay, what does it mean? The red line is going to be the posterior expected value, and the red region is going to be the expected value plus and minus 1 standard deviation. That represents what is our best current knowledge for what is going to be the temperature at each time point here. Okay, this is how we see we can filter out some of the noise associated with our imperfect observation and have a better estimate of what's the actual real temperature. Okay, this is going to be our first setup to approach the problem and build the mathematical formulation for these state space models. So a little more formally, in our basic problem setup, now we have a time series. So t is going to be our variable used to describe at which timestamp are we at. So going from 0 up to capital T, t being my lastest timestamp. So x of t is going to be what we call our hidden state. Okay, this is going to be the state of our system. In this case, it's going to be the temperature as a function of t, the time. So this is a deterministic yet unknown quantity, okay? as we put for in the case here, we need to say that this was the true temperature. Okay, the room has a given temperature at every point in time. So that temperature doesn't, at a given point in time, it doesn't vary. It's not a random variable, okay? It's a deterministic quantity. But what we want to do is to infer what is going to be our posterior knowledge for that temperature as a function of imperfect observation. So the output is going to be probabilistic because we have imperfect knowledge, okay? So xt, fundamentally, it's a deterministic quantity, yet our knowledge of xt is imperfect, okay? It's currently unknown. Y of t is going to be what we observe, the actual temperature observation we're doing as a function of t, the time of xt, okay, of the temperature. So yt is going to be xt, the actual temperature, plus v of t, and observation error. So this equation is what we call our observation model, okay? What is the relation between what we observe and the hidden states? In this case, we have a single hidden state, x of t, okay? So in this case, it's a simple linear equation. My observation is the current temperature plus an observation error, where the observation error is going to be a realization of a Gaussian random variable with mean 0 and standard deviation or variance sigma v squared. My transition model, xt, equals xt minus 1. So it means that I assume that my temperature in that room is going to remain constant. Okay, if ever it gets cool, the heat is going to turn on. If ever it gets cold, the heat is going to be turned up. Okay, so I assume that I'm going to have something that is nominally constant temperature over time. So knowing my temperature at time t minus 1, I assume that it's going to be the same temperature plus wt and error term. Okay, there can be an overcorrection from the heating system or an overcorrection from the air conditioning system, which will lead to these small fluctuation over time in the room temperature. And in this case, that wt, that process error in my transition model. So transition model is the one that allowed me to transit the transition of my hidden states over time. That transition error wt is again the realization of a Gaussian random variable with expected value 0 and variance sigma v squared, sigma w squared, sorry. And what we're trying to do, what we're trying to infer, is what is going to be my posterior PDF for xt, given all the observation from y1 up to yt, okay? Not only the current observation, but all the observation I've seen in the past, okay? And this, building on the linear function of random variable, as well as the Gaussian conditionals, we are going to obtain something that is that form. So our current posterior knowledge for xt is going to have as expected value, the expected value of xt, given all the previous observation, and we're going to have a conditional variance, which depends on the same thing. So we're going to look at how can we obtain these quantities. But before seeing this, we need to define a compact notation to keep the equation simple, okay? So in the long form, if I have a set of observation from y1 up to yt, I'm going to express this set in the short form as y subscript 1 semicolon t, okay? So that represents the set or a collection of observation from y1 up to yt. So the first index is the first observation, the last index is going to be the last observation. Okay, so if I want to express the conditional expected value of xt given y1 up to yt, I'm going to summarize this by mu of t given t, okay? So the first index on the left of the condition refers to xt. The second index on the right of the condition represent y1, always 1 up to t, okay? This is what this short form notation means. Then if instead of expressing my posterior expected value for y1 up to yt as it is here, it's up to yt minus 1, then it would become mu of t given t minus 1. And I have the same for the variance. Instead of expressing variance of xt given y1 up to t, is going to be sigma t given t. The first index refers to which hidden state. the second index up to what observation do I consider, and square here because it's the variance. Okay, so now we're going to look at how do we get from a prior knowledge for the temperature in the room here at time t equals 0 to my knowledge at time t equal 1, where I'm collecting my first observation. Okay, so at time t equals 0, let's assume we only have access to our prior knowledge. Okay, the expected value of x0 is equal to mu 0. And the variance of x0 is equal to sigma 0 squared. Let's assume this is the only information we have available. And note, in the case where you had no clue what your prior state is, in that case, you are going to use an arbitrarily large variance, and that's going to represent an absence of knowledge for your prior knowledge. Then, what we're going to do is that from our prior knowledge at time t equals 0, we're going to compute our prior knowledge at time t equal 1. Okay? So in that case, in order to propagate our knowledge at time t equals 0 to t equal 1, what we're going to do, we're going to use our transition model, because this is the transition model that expresses how our knowledge evolves over time. Okay? This links my knowledge time x0 to my knowledge times x1 by saying it's x1 is x0 plus w1, where keep in mind w1 is the realization of that Gaussian random variable, 0 mean variance sigma w squared. Then if I want to propagate my prior knowledge of what could actually be my observation at time t equal 1, I'm going to again propagate my prior knowledge that I've gained here into my observation model. Okay, the observation model relates what is the possible observation y1 given x1 and v1, where v1 is a realization of my observation error, which is Gaussian, mean 0, variance, sigma v squared. So I can calculate first what is going to be my expected value for my prior knowledge for x1 given my knowledge of x0. So in this case, little typo, x0 should be lowercase here. Because x1 is a random variable, x0 should be constant. So this is equivalent to the mu1 given 0. So mu1 given 0 is the expected value of x1 given x0. So in this case, it's going to be the expected value of x0. Expected value of x0 is mu0 plus expected value of w1. Expected value of w1 is 0. So the result is simply mu0. Then the variance of x1 given x0 is going to be the variance of x0. Variance of x0 is sigma 0 squared plus variance of w1, because both x0 and w1 are statistically independent. So I simply obtain the variance of the sum by the sum of the variances. So in this case, sigma 0 squared plus sigma w squared. Okay? So this is how I'm going to obtain my variance. So this is my prior knowledge at time t equal 1, given only my prior knowledge at time t equals 0. I haven't put any observation into play here. Then I can predict what is before observing my actual observation. What could that observation be? Okay, I'm going to make my forecast into the y space. And to do this, I currently have my prior knowledge for x1. This is what I have here by the expected value and the variance. I want to predict forward what could be y. So then it's going to be the expected value of x1. So it's going to be mu10 plus the expected value of v1. Okay, in that case, the expected value of mu1 given 0 is mu0 plus expected value of v is 0. So it's simply mu0. The variance of y1 given y0 is going to be the variance of x1. So variance of x1 is sigma 10 plus the variance of v, sigma v squared. So sigma 1 given 0 plus sigma v squared. And sigma 1 given 0 is sigma 0 plus sigma w squared, which make the variance of y1 given my prior knowledge at x0 is going to be equal to the product of these three terms. The initial variance for what could be the temperature, the initial variance for my observation, my transition error, and my variance for my observation error. And finally, the last term I need to calculate, what is the covariance between x1 and y1? Okay, my covariance between x1 and y1, the term that is in common between the variance of y1 and the variance of x1 is that sigma 10. This is the term I have here. So sigma 10 is sigma 0 plus sigma w squared. Perfect. So now, from all the quantity I have defined here, I can represent at time t equal 1, what is my joint prior knowledge between x1 and y1. Okay, and this is what I'm doing here. I'm building my expected vector, which is for mu x and mu y, so my two expected values I've computed previously. I can build my joint covariance for x1 and y1. So I build that covariance matrix where I have my variance for x1, variance for y1, and covariance terms that are on my diagonal terms. So in this case, if I actually end up observing y1, I want to use that observation in order to update my quantity for x1. And doing this, I can use the Gaussian conditional we've seen earlier to obtain my estimate for mu1 given 1 and sigma 1 given 1. And to do this, I use the same Gaussian conditional equation we've reviewed together earlier. And all these terms in these Gaussian conditional equation are function of the quantity we have here that we've calculated earlier. The only new quantity that comes here is y1, where y1 is the actual temperature value I'm observing during my measurement step. Okay, so that was to go from my initial knowledge at time t equals 0 to my knowledge at time t equals 1. So now what we want to do is just repeat the same thing, but to generalize this, to transit from any state t minus 1 to any new state t, okay? So we are going to say that from my posterior knowledge at time t minus 1, I want to use the transition model between the step or the hidden state t minus 1 and t, as well as the observation model between xt and yt, in order to compute my prior knowledge at time t. So my expected vector, what is it going to be? It's going to be my expected value of xt given y1 up to yt minus 1 is going to be just before equal to mu t. This is the short form notation, mu t given t minus 1. And here is going to be simply the sum of my expected value at time t minus 1. So this is the posterior expected value at time t minus 1. So this is the expected value of x t minus 1 given y1 up to t minus 1 plus the expected value of wt, which is again 0. So this is only this quantity. The same thing for the variance. So this is the long form, this is the short form. This is going to be the sum of the variance of my prior knowledge. So sigma square t minus 1 given t minus 1 plus the variance of my transition process, sigma w square. The expected value of y is equal to mu t given t minus 1. This is again the same thing. Why is it this? It's because here we have our prior knowledge for xt. So it's going to be our prior expected value for xt, which was mu t given t minus 1 plus the expected value of vt, which is 0. So it remained mu t given t minus 1. And the variance for yt given y1 given t minus 1 is going to be our prior knowledge for the variance here. So these two terms here, plus the variance for my observation process, okay? Where these terms here represent the variance for t given t minus 1 for my y variable. Okay, and my covariance between x and y is going to be the term that is common to both variance of y and variance of t, is that sigma t given t minus 1. So the sum of these two terms here. Prior variance for xt minus 1 and variance for my transition process. Okay, I can again build my joint knowledge for xt given all the data up to t minus 1, yt given all the data up to t minus 1 by this expected vector and covariance matrix, where all the quantities that are involved here are the quantity we derived here. So in that case, if I want my posterior, so I want to use my observation at time t in order to update my knowledge of xt, okay? To do this, I'm going to obtain here, again, my normal formulation for xt, parameterized by the expected value and the variance, where the expected value and variance are still obtained using the same exact Gaussian conditional formulation. Perfect. So let's apply this formulation we've done on that temperature example. So we have the same example. We're tracking the temperature over time, over a span of 5 hours. So this is the reality. we're going to have access to some observation, and we want to retrieve this expected values and this confidence region across time. Okay, so we have xt, the temperature that is evolving on a time span of 5 hours. So t goes from 0 to 5, 0 being only our prior knowledge. Let's assume that here our prior knowledge was simply that the expected value was 10 degrees Celsius and the standard deviation is 2 degrees Celsius. This, keep in mind, doesn't represent the variability of the temperature. This represents the uncertainty associated with our current knowledge of what the actual temperature can be, okay? We have the observation model, yt equals xt plus vt, where here my observation errors is described by a normal distribution with expected value 0, variance 2 squared, okay? This is what I have here. No, this is not what I have here. This is for my uncertainty. This is the observation process standard deviation. This is my initial uncertainty of what could be the temperature at time t equals 0. I have also my transition model. So we say that xt equals xt minus 1 plus wt. My model error is 0 mean and standard deviation 0.5 squared. Okay, so now we're going to break down and do that recursive updating of our knowledge. So it's always the same step: predict, observe, update. Predict, observe, update. So I start at time t equals 0 using only my prior knowledge of what do I have here. So at time t equals 0, we said that my expected value is 10. My standard deviation for what could be the temperature is 2. Okay, so I can project forward at time t equal 1 what could be my expected value and variance. So in this case, if I predict at time t equal 1 what it could be, my expected value of xt given t minus 1 is equal to my expected value at time t given t minus 1 is 10. My expected value for the observation y is 10 as well, because both the transition model and the observation model, the error terms for w and v are 0 mean errors. Okay, so the expected value remains the same. So what we see here on the graph, the dark blue confidence region represent my prior knowledge for xt in terms of expected value plus and minus standard deviation. Remember at time t equals 0, we said that the expected value was 10, standard deviation was 2, so variance 2 squared was 4. Okay, this is what I have here in that blue region. Then I can predict forward what is going to be my expected knowledge or my expected value in variance at time t equal 1. So my expected value for x and y are going to be the same, 10 at time t equal 1. My variance, though, is not going to be exactly the same. So my variance at time t equals 0 was 4. My variance at time for xt given t minus 1 is going to be my prior variance, which was 4 plus sigma v squared. Okay, so 4 plus 0.5 squared. This was sigma w was equal to 0.5. So sigma 0.5 squared, it's 0.25. That gives me 4.3. My variance for y is going to be my variance for x plus my variance for v, where sigma v is equal to 2. So it's going to be plus 4, 8.3. Okay, and this is what we have here. Okay, so what I have here is my mean plus and minus standard deviation. I add 0.25 here at time t plus 1 for my transition error, and I add in green, this is my confidence region for the actual observation value. So in this case, since I have a relatively large uncertainty, it adds up a lot on the uncertainty. And what we have here in that representation is my joint PDF for x and y. X being the actual temperature, y the observation of the temperature. So what you see here is the marginal x is this axis, y is that axis. You see the marginal PDF for x, marginal PDF for y, and the surface represents the joint PDF for x and y. And here you can see the PDF is kind of squashed because of the positive correlation between x and y. And if we calculate that correlation, it's going to be here 0.72. Okay, perfect. Then what we're going to do, we're going to update this knowledge by taking a slice in that joint distribution. Okay, my actual observation at time t equal 1 is equal to 7.1. Okay, this is the actual observation. So I take a slice in that joint PDF, but just as before, that slice in the joint PDF won't normalize. It's not a PDF. In order to normalize this slice, I need to divide by the marginal probability for f of y. And this is what leads to the conditional PDF we see here, okay? In this case, I saw the PDF for f of x given y, and we see the pink region, which is my confidence region for that posterior knowledge here. And we can obtain the expected value and variance for this posterior knowledge being 8.5 and 2.1. Okay, so this is the posterior expected value and posterior variance. So you see the expected value of 8.5 is the point I have here, plus and minus 2.1, the square root of 2.1, which represent plus and minus 1 standard deviation. So this is my current knowledge at time t equal 1 for what the actual temperature could be. The reality is the blue line, my expected value is the red one, the confidence region is the pink or the red shaded region. Then what I do is I take my current posterior knowledge and it's going to become my prior knowledge for time t equal 2. So in that case, this was my posterior knowledge at time t minus 1. I predict ahead. So I'm going to predict here, given my previous knowledge at time t equal 1, what is my prior knowledge at time t equal 2? Okay? So I do the same calculation as I did before. And if I look at the numbers and I represent this number, I have again the marginal PDF for yt, in that case y2. I have the marginal knowledge for x2. And this is the joint PDF. My actual observation is somehow around here, so somehow around a little above 12. Then what I'm going to do, I'm going to take that slice corresponding to the observation, 12.3. I'm going to normalize this. It gives me that posterior knowledge. So the same width I have here is the same width of my confidence region here at y equal 2. In that case, the expected value is 9.9, variance is 1.5. This is what's represented here. The expected value is 9.9 plus and minus the square root of 1.5. So even if my observation is there, my current knowledge of the temperature is really close to the true temperature, but it's still uncertain as represented by this confidence region. I'm going to do that over and over again. I take the posterior knowledge at time 2, it becomes my prior knowledge for time 3. What I do, I pass that prior knowledge through the transition model, through the observation model. So my two confidence regions are again represented here. I observe the value, I update my knowledge, and I do that over and over again. So I'm going to have my prior posterior that becomes my prior time now 3. I pass this in my transition model. I observe, I update, predict, observe, update, and I go that forward. Okay, so you can see that even after a 5 time step, I could have a good rough estimate of what's the actual temperature, even if my observation process is widely variable. Okay, I can filter out that noise using that Gaussian conditional equation. Okay, this is the core principle behind what we're going to use as method in order to analyze time series data. Okay, so now let's add one layer of complexity in our analysis. So we're going to look at a model that is a notch more complex. In this case, we're going to look at the temperature in a room where imagine the air conditioning is broken and keep shooting cold air so that over time the temperature keeps dropping. Okay, this is how it's illustrated here. Over a span of 10 hours, we see that there's a linear downward trend that represents the drop in temperature, going from plus 10 degrees right now up to something about minus 13 or 14 degrees on a span of 10 hours. So in that case, we want to use state space model in the context where we have not one, but two hidden state variables. The first one being the temperature, the second one being the rate of change. So in this case, we want to both jointly infer. So from the actual observed temperature, we want to use this observation to infer both the current temperature as well as the rate of change over time. So we see that the truth is the blue line. Our estimation is again represented by the red dots, which represent our expected value, as well as the red confidence region for both the temperature and its rate of change, so the speed of the temperature change. So in that case, our vector of hidden states is going to contain two variables. The first one being xt, the temperature. The second one, xt dot, which represent the rate of change of the speed. So we're going to look at this on the time span of, say, 5 hours. So our observation model, we're going to say that yt equals xt plus vt, same as before. So in that case, we say that we don't observe the actual rate of change of the temperature. The only thing we're actually observing is what is the current temperature. And we need to infer what is the rate of change. We're never going to actually directly observe it. So in that case, we can express this in a vector notation or in a matrix form. In that case, we're going to have a f vector, which is 1 and 0 that multiply xt, or vector of hidden state. So my observation yt is 1 times xt plus 0 times xt dot, the speed. Okay, so it's implying that the speed is not observed. It doesn't contribute to yt. Here we still have an observation error vt due to our imperfect observation process. So we can model this as a system of equation. We can say that we have a transition model for the hidden states, saying that my temperature over time is assumed to be locally decreasing, so linearly decreasing. So we're going to say that my temperature at time t is equal to my temperature at time t minus 1 plus my speed, so x dot t minus 1 times delta t plus wt. Again, an error term associated with the fact that this linear decrease in time is not perfectly describing my reality. And what is the transition model for my speed over time? We assume that our temperature will decrease at constant speed. Okay, we don't know what the speed is, but we know that if we would know the speed, the best model to describe that change over time would be a linear model. So, or in this case, a constant model for the speed, so that xt dot equals to xt dot t minus 1 plus wt dot, where wt is the process error associated with this model that controls how does my speed change over time. I can represent this system of two linear equations in a matrix form by saying xt, which is my vector of hidden state at time t, is equal to a, which is a matrix, times xt minus 1, my vector of hidden state at time t minus 1, where a is 1 delta t. These are the coefficients here, 1 delta t, 0, 1, because 0 times xt minus 1, xt minus 1 is not there. So this is just summarizing this linear system of equation into a xt minus 1 plus wt, a vector of wt dot. So this is the matrix form generalization of my transition model. So at the end, from everything we're going to deal with from now on, we have two things: the observation models, the transition model. The observation model always take that form, yt equals f of xt plus vt, okay? Where ft control which of my hidden state xt contribute to my observation vector yt. And we have our transition model, xt equals a xt minus 1 plus wt, where a is the matrix that say how is my transition process between my variable in xt and those in xt minus 1. And where, keep in mind, wt is my observation errors, wt are my transition process errors. Okay, so we're going to formalize this. How can we go from a step t minus 1 to t? Okay, so the first thing, we're going to compute our prior knowledge at time t from our posterior knowledge at time t minus 1. And we're going to do this by propagating forward our prior time t minus 1 through our transition model. Okay, so where I have my prior knowledge for xt minus 1, I know that my error here is a realization for that joint normal process, expected value 0, covariance q. And I have also my observation model, y equals f xt plus vt, where the covariance for my observation errors are r. Okay, so there are four matrices that describe this observation and transition process: a, f, q, and r. So here, my expected value, mu t given t minus 1, is going to be equal to A mu t minus 1 given t minus 1, okay? I'm going to simply say it's going to be my expected value evaluated in that process where I only have A mu t minus 1 given t minus 1, my posterior expected value for xt at time t minus 1, given that the expected value for wt is 0. My covariance at time t, given all the data up to t minus 1, is going to be A times my prior covariance for xt minus 1. So xt minus 1 given t minus 1 times A transpose plus Q, my covariance for my error process. My expected value for y, given all the data up to t minus 1, is going to be F times mu t minus 1 given t minus 1. And my covariance for yt, given y1 up to t minus 1, is going to be F. Covariance for t given t minus 1, F transpose, plus R, where R is my covariance associated with my observation noise. So keep in mind, typically R is going to be a diagonal matrix. Most often Q is not. We're going to come back to this later on. Okay, and my cross covariance between X and Y is simply going to be my covariance I have here for xt given all the data up to t minus 1 times F transpose, which is my observation matrix here, which is F. Okay, so in terms of notation, we say A is going to be my transition matrix, F is going to be my observation matrix, my error covariance, my transition error covariance, my observation error covariance. Okay, so based on that knowledge, I can define all of these equations. And all of these equations allow me to build my joint knowledge for my joint vector x and my joint vector y. So I can concatenate my expected vectors, I can concatenate my covariances. And now if I want to build the PDF for my joint knowledge of xt, given all the data from y1 up to t minus 1, it's obtained through that conditional, which has this closed form solution, which is a multivariate normal defined by the conditional expected value, conditional covariance, which again follow that same Gaussian conditional equation, where now I have a vector of observation yt. Okay, and if we just put together all these equations, all the steps we've done, actually if we just reorganize them, what we're going to obtain is the classic Kalman filter equations. Okay, the classic Kalman filter equation are divided into two steps. The first one is the prediction step. Okay, it's the same as we had before. We just propagate forward using our transition model from our prior knowledge at time t minus 1 to our prior knowledge at time t, given all the data up to time t minus 1. Then what we do is that we use the measurement step, where we combine all the steps that we've done before. So these steps have different names, but we don't really care here about what is the name of these steps. This is just a compact form of exactly what we did step by step together. Okay, if you were to recombine all these steps, you would get exactly the same things as we've obtained step by step together. Okay, and keep in mind that what we've done is actually derive the equations behind the Kalman filter. So we're going to apply these equations in order to obtain these results. So we know that the underlying truth is the blue lines, either for the temperature and the rate of change, so the speed. And we have access to these actual observations, so the pink dot. And even if we never actually observe the speed, we're going to see that even if we start from an erroneous but quite broad prior for what could be the actual initial speed, we can go, as we collect more and more data, we can infer the speed, even if we never have actually observed it, at least not directly. Okay, so again, to formalize this context for this problem, we have a vector of hidden state, xt and xt dot. Okay, my two hidden state, the temperature and its rate of change. And I want to track this problem for a time span from t equals 0 to 5 hours. I have my observation model. So keep in mind here how I want to express this in a vector format. F is my observation matrix, 1, 0. So it's going to be 1 times xt plus 0 times xt dot. Xt dot is never observed. My transition model, I can express that as a system of linear equation. I can generalize this as xt equals a xt minus 1 plus wt. So what my temperature is the temperature at time t minus 1 plus delta t times the speed, or the rate of change, same thing. And the rate of change is constant over time, except for the transition model error. Okay, so this are summarized here. My observation model, my transition model. I simply need to define what is my actual prior knowledge at time t equals 0. So now I not only have to define my prior knowledge for what's the actual speed, for what's the actual temperature, but also what's the actual speed, okay? So I have to define an expected value in standard deviation for both the temperature and its rate of change. So for the temperature, the expected value, let's assume it's 10 degrees Celsius, the standard deviation is 2 degrees Celsius. The same thing for the speed. My expected value for speed, I don't know if it's positive or negative. I don't know if it's the heating or the air conditioning who's broken. So expected value is 0 degrees Celsius, standard deviation is 0.5. So this is the prior knowledge for temperature, prior knowledge for its second line rate of change. And let's assume that my prior for the temperature and its rate of change are statistically independent so that the correlation coefficient is 0. That allows me to build my prior expected vector and prior covariance for my joint knowledge for the temperature and its rate of change. So we see 10, 0, this is 10, 0. So my standard deviation square, so 2 square, 0.5 square, and 0 correlation, so 0 term on my off-diagonal terms. Then I need to define my matrix R and Q. So R, this is my standard deviation for my observation process. So let's assume the standard deviation is equal to 2. And my covariance matrix Q, which define the covariance for the error process, the joint error process for the temperature and its rate of change, it takes that standard form. Okay, we're going to review that standard form in the next module, where we're going to look at the definition of linear model for state space model. So right now, just assume that this is the covariance matrix, where sigma v square here is equal to 0.1. Okay, if we combine all these information together, we can do it. So we can predict forward what is our knowledge, we observe, we update. So at time t equal 1, this is the updated value we would obtain. So the truth, again, remember, it's the blue line. Okay, so I have a really close estimate for the temperature. I have a really broad estimate for the actual speed because I don't observe it directly. My posterior expected value is the red dot. My posterior expected value plus and minus 1 standard deviation is that red confidence region. Then, and this is my actual observation. I'm going to have predict, observe. So this is my prediction for the temperature. We see that the dark band is my prediction for my hidden state. The green band is the expected value or the confidence region for my observation. So it's always wider because on top of the hidden state, I also have the observation error process. Okay, so I predict this and I predict forward here for the speed. Okay, we see that we don't have a green confidence region here because I don't have any observation. So I don't predict forward what could be observation. There are no observation for the speed. Then I have my observation. I'm going to update. Predict, observe, update, predict, observe, update. And I go forward like this, always doing recursively the same step over and over again. So we can see that I can both infer here my temperature over time, even if I have noisy observation, but as well as I can infer my actual speed. Even if I never observe the speed, I can deduce the speed from my conditional updating step using that Gaussian conditional equation. Okay, so now let's see what kind of task can we do with this. Okay, we're going to see the task other than just estimating the hidden states. So we're going to look at how can we differentiate the term forecasting and smoothing. So what we've done so far is the task of what we call filtering. Okay, the same thing as we call it Kalman filter. Why do we call Kalman filter? Is because you could see it as a way to filter out the noise you can have in your process. Okay, you can filter the signal from the noise. Okay, this is one thing you can do with the Kalman filter, but it's much more general than this. Okay, so the task of filtering, what you're going to do is that you're currently at time t. And what you want to do with Kalman filtering is to obtain the best estimate possible at time t for your hidden states, given all the knowledge for y1 up to yt. Okay, this is what we call the filtering task, having the best estimate at time t given all the past knowledge. If we want to do smoothing, smoothing is not the same thing. So we don't have data only from time equals 0 up to t. With smoothing, we have data from time equal t equals 0 up to capital T. And what we want is to use the data before and after our time t to get the best estimate. Okay, so use data before and after what we're looking at in order to have the best estimate for state t. And in forecasting, what we want to do, we're still at time t. We have data only for the past. So from time 0 up to time t. And what we want to do is to forecast n time step in the future, what is going to be my current state. Okay, so what we've seen so far is filtering, using past data in order to have the best estimate possible for the present. What we want to look at is how can we do smoothing, use past and future data to estimate the current state, or forecasting. How can I predict in the future in the case where I don't have data yet, okay, to forecast what is upcoming. So first, let's look at forecasting because this is the simplest. So if we want to forecast n time step in the future, the only thing we need to do is to recursively use our transition model over and over again, okay? So we have our current state of knowledge at time t. We're going to use our transition model. We're going to get our prior knowledge at time t plus 1. We're going to use that prior knowledge without updating it with observation because we don't have observation yet. We're going to pass it again into our transition model to get our prior knowledge time t plus 2, t plus 3, t plus n, okay? So this is what we want to do. And in this case, in order to obtain going from time t up to time t plus 1, I simply use my forward propagating equation obtained through my transition model. So it's going to be a times mu t given t, a sigma t given t, a transpose plus q, okay? And basically when we forecast is the same thing as applying the Kalman filter step, but without doing the update step. And here, one very practical thing that we can use that for is that when actual data is missing, it's the same thing as forecasting. So it's really, really common when you analyze real life time series data to have missing data because either sensor failure or because data logging failure or millions of reasons. But I tell you, for having done it very often, we have missing data. This is super common. In this case, how do we handle missing data? Never go and manually enter a value. What you would do instead is just treat the missing data as a forecast. So you're going to predict that value and you're not going to do any update and you're going to carry on until you have data. So intrinsically with the state space model, missing data is simply considered as a forecast step. So you're going to predict forward without updating using the Kalman filter. So very convenient for practical applications. So now let's look in practical terms. How do we make forecast? Okay, we have the same prior knowledge for our second example. So we have the air conditioning who's broken. We have temperature that's linearly decreasing over time. So in that case, I have here my observation model, my transition model, the same prior knowledge as I have before. So same prior mean vector, same prior covariance, same covariance matrix R for my observation error, same covariance here for my transition error. Okay, so now we want to forecast temperature. We're going to start by collecting some data up to time t equal 4. And then up to time 4, what we do is that we don't have any data anymore. Okay, we've collected data for 4 hours, and then we don't have any data. The only thing we want to do is to forecast forward what is going to be our process in the future. So what you can see here is that beyond 4 hours, I don't do any update step simply because I don't have any data. Okay, so we can see how we can forecast over time by recursively always using the transition equation without ever updating. Okay, so this is the forecasting step, how we can do it. The second thing we can do to extend our capacity is to do smoothing, meaning using data from the past and the future in order to obtain a current time here. So Kalman filtering, what we did earlier, is something that is intrinsically online, meaning that he can analyze data as you collect it. Okay, smoothing is something that is offline. Okay, you don't do this as you collect data. Typically, you're going to do this, you're going to have a large sequence of data, and you want to obtain the best estimate for every time step in your whole time series. In that case, you're going to use smoothing. Okay, so the first step to do filtering, the first step if we want to do smoothing is to do filtering. Okay, exactly what we did before. We're going to go forward, predict, observe, update. Predict, observe, update. And this is what we do forward, going from time t to t up to capital T, the last time step in my time series I have available. Then what we have to realize is that intrinsically, the last time step in my time series, my knowledge is based on more data point, okay? Because it has all the data collection from time t1 up to time t minus 1, plus my prior knowledge at time t0. Whereas here, my knowledge at time t0 is not based on any data, it's just based on prior knowledge. So in that case, what I want to do is do the backward operation of propagating backward my knowledge from time t equal 1 up to time t equal t over all my time steps. Okay, so for instance, at time t, this estimate contains all the data from the past, but no data from the future. Okay, this is what Kalman smoothing allows to do. Take all the data beyond that point and propagate it on that time. So what we're going to do is that we're going to go backward. Now we're going to use the posterior knowledge at time t and use it to update our knowledge here at time t minus 1. And then we're going to move back like this forward or backward in time. Okay, so in that case, that last would be treated as an observation to update this one. And we go back recursively like this in time. And at the end, this is what we obtain, or what we call our smoothed estimate. Okay, and if we look at the RTS Kalman smoother, this is the typical formulation to do that smoothing. So here we can obtain the expected value of mu t given capital T. So we want to obtain our best estimate at time t given all the data before and after by recursively applying this step where J here is given by this formulation. So J here is not the Jacobian, okay? It's just, this is a term that designed by definition these matrix here, where we're going to recursively treat the last estimated step as an observation and go back. When we update this one, we're going to use this one as the observation and move backward. Use this one as an observation, move backward recursively. Okay? So this is how we can proceed if we want to do smoothing. So let's look at our problem that we have now. So we have a single hidden state xt. So we're not in the case where the air conditioning is broken. We're in this state where we assume the temperature is steady over time. Okay, over a period of 5 hours, the prior expected value is 10 degrees Celsius. The prior standard deviation is 7 degrees Celsius. My observation model yt equals xt plus vt. My observation error, the standard deviation is 1. My transition model is a linearly constant model. My transition errors have a standard deviation of 0.5. And this was the result I obtained from filtering. Okay, so the reality was, again, this is time from 0 to 5 hours. The vertical axis is the temperature. So the truth is the blue line. The observations are the pink diamond. And the expected value, posterior expected value, would be the red circles. My uncertainty associated with this estimate would be the red shaded confidence region. Okay, so this is what I obtain through time as I collect more and more data. And notice how the confidence region shrinks over time as more and more data is collected. Okay, now what would happen if I would do smoothing? I would propagate that information backwards. And this is what we see here in that kind of that cyan color or turquoise color line and confidence region. So you see that for the last step that I've observed, filtering and smoothing give the same result. There's no information in the last step that was not already considered. So there's no change for the last step. However, for all the other steps, you see that I have a little more knowledge in that confidence region, so it shrinks. I have a little more knowledge here, it shrinks and it shrinks. And the more I go back in time, the more my estimate shrinks, and you see it goes towards the true value. Okay, so you see that by doing smoothing, I have a better estimate for what my actual hidden states are than just going forward with my estimation for my data. Okay, so now there are some issues we've overlooked. Notably, is that we've always assumed that we know what is sigma v. And we've always assumed, for instance, what if sigma w. But in practice, you might not know these parameters. So you need to learn them from data, okay? So here, we still have parameters into those state space model. How can we learn these parameters from the actual data we're seeing over time? So first, to learn the parameter, we need to define how to quantify the performance of our model conditioned on the parameter value. Then we're going to look, how can we use a simple maximization approach in order to learn these parameter values. So first, how do we measure the performance of a model? Okay, so to do this, it's going to be through the marginal prior probability of each observation. Okay, what does it mean? I use all the data up to time t-1 in order to predict what could be my actual observation at time t. So this is using all the data up to at time t-1 to predict, okay, at time t, what is going to be my actual observations? So that means the expected value is f times mu t given t-1. So this is the prior knowledge for the hidden state times here my observation matrix. This is my prior covariance for y. And then this is the marginal prior probability only at time t. Okay, what's going to actually measure the performance of my model? It's not only the performance at one time t, it's the collection of the predictive performance at all time. So my likelihood is going to be the product of my marginal prior probability at all time, because we assume that conditional on the hidden state value, my observations are actually independent of each other because my observation errors are themselves independent. So it means I can build my joint PDF for all my time step for what could be my actual observations by taking the product of those marginal prior probabilities. But keep in mind, we have already seen that issue. Here, that PDF for that marginal probability is most likely going to be smaller than 1. And actually, it's most likely going to be much smaller than 1. What is going to happen if I take the product of a lot of terms that are smaller than 1? Quickly, I'm going to reach 0. Okay, I'm going to have 0 underflow issue if I take the product of several terms that are smaller than 1. So in order to solve that issue, what we're going to look at is the log likelihood. So we take the log of our marginal likelihood and we sum them over all our time step. So we're not going to have that 0 underflow issue if we take that procedure. Okay, so let's look at the step of how do we calculate our log likelihood in the example I've shown earlier. So we look at the example where we have a roughly constant temperature over time in our room. So what we want to do is to estimate the temperature xt over a period of 5 hours using imprecise measurement made every hour from t equals 0 up to 5. Okay, again, prior expected value 10 degrees Celsius, prior standard deviation 7. We have our observation model, we have our transition model. Exactly the same dynamics, the same parameters as before. So in that case, what we have here was the prior knowledge. So expected value 10, variance 7 squared, so 49. So this is what I have here. So my prior expected value, prior variance is given here. It's really, really large. Okay, I have a lot of noise here. This is my actual observation at time 1. So the operation to calculate my prior expected value for x and y are exactly the same step as before. But now I'm going to represent explicitly what is the marginal PDF for yt given y1 up to t minus 1. So in this case, it's f of y1 given my prior knowledge. Okay, so this is my PDF. what I have here as a green region is the same as what I have here as my green region, okay? This is the standard deviation, so the square root of what I have here, the square root of 50.3, okay? The expected value plus and minus the square root of 50.3 represent that green region. So in that case, the pink line here is the actual observation at time t equal 1. This is that pink diamond, okay? The height of my marginal PDF for yt, given all the data up to t minus 1, the height here, which is roughly 4 to the power 10 to the minus 2, so 4 times 10 to the power minus 2 is my actual here marginal likelihood, okay? How likely my model was to predict that actual observation, okay? If I take the log of this quantity, it's going to give me minus 3.29. So the joint log likelihood from time 0 and time 1 is 0, what I had before, minus 3.29. Okay, then, okay, I update, I predict ahead. This is my new marginal prior knowledge for y2 given all the data up to y1, okay? So in this case, I look at what was the prior density of observing that actual data. This is 0.27. So this is my marginal probability density. I take the log minus 1.32. Before I add minus 3.29, I'm going to add minus 3.29 minus 1.32 minus 4.61. Okay, this is my joint knowledge, my joint prior knowledge for observing x1 and y1 and y2. Then I do the same for y3. This is my joint prior knowledge for y3. What was the prior probability of predicting y3? This is the actual value, 0.19. I take the log, I add it. y4, y5, etc. Okay, so this joint log likelihood is actually the quantity that's going to measure the quality of the model at predicting ahead the data given my parameter value. If I would have used different model parameters than those that I've used here, I would have obtained either a worse or a better performance by looking at that quantity here. Okay, so how do we learn about what are my optimal parameters, say for sigma W or for sigma V for a model? I do this by looking at maximizing my log likelihood. So we're going to use a maximum likelihood estimate here, where our optimal parameter value for, say, sigma W and sigma V are going to be the argument theta that maximize my log likelihood for all my time steps. So here, what I say this or I say this are equivalent, because always when I calculate my log likelihood, I'm always implicitly depending on my parameter value. Okay, to calculate my log likelihood, I need to define those parameters. So I'm implicitly, intrinsically depending conditionally on those parameter values. So what I'm trying to do is to maximize that log likelihood. So I'm trying to find a point where the derivative of my joint log likelihood is equal to 0. And to do this, we can use any maximization algorithm, such as the gradient descent or Newton-Raphson we've seen in class. Okay, so now the last thing I want to see in terms of theory is how can we have multiple regimes competing with each other in order to detect regime changes online as we collect data. And this concept is governed through the switching Kalman filter, okay? So the key with Kalman filter and Kalman smoother is to analyze time series that are stationary or trans-stationary. Okay, what does it mean? In this case, the data is stationary. It's a constant speed or zero speed model. In this case, the data is trans-stationary. What does it mean? This model is also constant over time in the sense where the speed is constant over time. The condition is locally changing. So these can be named as stationary or trans-stationary. However, this we cannot apply our current Kalman filter theory. Why? Because part of the data we have one dynamic, and part of the data we have another dynamic. Okay, we cannot do this with the formulation we have seen so far. We can, no problem, analyze this. We can, without any problem, analyze this. But we cannot have, so far, a regime change like this, okay? And we can do this using, what we're going to see is the switching Kalman filter. So what we want to do is that each time, not only estimate the hidden state for our system, but also estimate what is the probability of each regime. Either here, the zero speed model, or here, the constant speed model. Okay, we have data as we saw at the beginning of this module, where we have here a constant speed regime, a zero speed regime, and here a constant speed regime. What we want to do is to make that inference, okay? Expected value plus confidence region, which would really capture the underlying phenomena, which has a zero speed model, constant speed model, okay? And we see the underlying reality was this. The dashed line was the truth, okay? And we see it took us some time that we end up understanding that actually the prevailing dynamics of the model I have here, it's not anymore a constant speed model, a zero speed model, it's now a constant speed model, okay? And we want to do that in real time and estimate here that the probability of the regime 1, which was the zero speed model, now drops to 0 because the constant speed model is now more prevalent or explain better the actual data we're observing. So now let's look in more detail at that switching Kalman filter algorithm, the notation, and also how do we put together all these things. So let's go from our prior knowledge at time t-1. Okay, so here the notation is that we have several models that we put in competition. Right now we're going to limit ourselves at 2 models competing with each other. So here my model 1 is going to be denoted by the superscript 1. Here I have 3 quantities I need to define: the expected value, the covariance, and the probability of that regime. Okay, so this is again the same notation as before. All the data for my expected vector at time t-1, given all the data up to time t-1. Same for covariance, same for probability. So here it means expected value of xt-1 given y1 up to time t-1, and that the regime at time t-1 was equal to 1. Okay, so this is my expected value for my first regime. This is the same thing, covariance for my first regime, and this is my probability of actually being at that first regime, given all the data I've seen up to time t-1. Then I have exactly the same quantity, but now with a superscript 2 to indicate that this is the same thing, but now for the model or the regime 2. Now what I have is that at each time step, I can branch out into 2 different models. So in there, I performed a filter operation with model 1, say one that's going to be zero speed model, or model 2 that could be a constant speed model. So I assume that at time t-1 at a constant speed dynamic, and then either I keep being in a constant speed dynamic or I switch to a linear change in my speed. Okay, so in this case, if I say I was in a zero speed dynamic, I assume that I keep being in a zero speed dynamic from time t-1 to t. I do the update equation. That would be my posterior mean vector, posterior covariance, and my likelihood. Okay, this is the likelihood of actually observing yt, given that at time t-1 I was in state 1, and I transit between time t-1 and time t through the model 1. Okay, the one with the zero speed model, for instance. Then I could have transit through the second model. Okay, so I was in a constant speed model at time t-1, but I assume that now I have a regime switch. I depart from the zero speed model and I go with a constant speed model. So this is the expected value given that I was at time t-1 in the regime 1, but then I have switched to regime 2. And I have the likelihood of at time t-1 I was in regime 1, I transit to regime 2, given all the data that I know. What is the probability of observing the actual data? Given that I was in regime 1, I transit to regime 2. And then I have the same thing for model 2. And that what we're going to do is that in order to avoid the explosion of the number of possibility, because if for each possibility we divide by 2, we're going to have an exponential growth in the number of combinations we need to consider. What we're going to do is that we're going to merge these possibilities. So all the possibilities that transit through the same model, we're actually going to combine them together. We're going to join them together to obtain a single expected vector, single covariance, and single probability, where this merge step takes into account the likelihood of each path and the prior probability encoded in that Z matrix of being at time t minus 1 in regime 1 and transiting to regime 1. The probability of being at time t minus 1 in regime 1, transiting to regime 2. And we have all combinations here. So at the end, at time t, what we're going to have is the same thing, 2 expected vector, 2 covariance, and 2 probability associated with each regime. And then we do the same mechanics again, splitting into 2 possible transitions for each of my model, merging and repeating over and over again. So if we look in more close detail, how does that merge steps operate? Okay, so now what we want to do is to merge both model that transited through, or both quantity that transited through the model 1. So we take these 2 quantities and we want to merge them in a single expected vector, covariance matrix, and probability. And to do this, we're going to use the concept of mixing Gaussian random variable, a Gaussian mixture. So here's an example. We have here the red distribution, which is a normal PDF, with mean expected value 1, standard deviation 1, and we say that the probability of that distribution is 0.9. If we have another distribution, expected value 3, standard deviation 1, and we assign a probability for this distribution of 0.1. What we want is to calculate what's going to be the expected value and variance of a normal distribution, which is going to describe here the sum of these 2. Okay, in that case, it's going to be that red distribution, for which the expected value is going to be pi 1, so the probability of the first distribution, times mu1 plus pi 2 times mu2. For my Gaussian mixture variance for the green distribution is going to be pi 1 sigma 1 square plus pi 2 sigma 2 square plus pi 1 pi 2 mu1 minus mu2 square. Okay, so here the variance is function of the respective variance plus of the square of the distance between the 2 distributions. So even if the 2 distributions would be very narrow in terms of distribution, if they are far apart, the distribution of the variance of my mixture can be really large. So here's an example. Here's another. I have 2 distributions here which have both the same variance. Here's the variance for my Gaussian mixture, which is larger, so 1.7 in comparison with 1 for the other 2 distributions. And this increase in variance is due to the spread in the distribution for my red and my blue distribution. The farther apart my distribution are, the more widespread my Gaussian mixture is going to be. On the opposite, if the 2 distributions are overlapping, my Gaussian mixture is going to be exactly equal to my 2 distribution. Okay, so this is this Gaussian mixture step that allows us to merge those 2 knowledge into a single Gaussian distribution. So I'm going to skip the detail. If you want more detail, go directly see in the book. All the steps to do that Gaussian mixture are explicitly represented. So now if we just apply it to look roughly how does it works, we're going to apply it to this example where we have temperature over 1 year for 1 year of data. Vertical axis is temperature. And we have to define first what is our observation model. So in this case, we assume always that we have a locally constant model. Okay, locally constant speed model. So it means we have always, in all cases, 2 hidden states. Okay, we're going to refine this. So our 2 hidden states are for the temperature and its rate of change. So here my observation model, my F matrix is 1 and 0 because I only observe the temperature. I don't actually observe its rate of change. Okay, my observation error here, the standard deviation is going to assume to be 0.5. My expected vector for my prior knowledge for what could be the temperature and its rate of change is 10 and 0. My prior covariance, 1 and 0.1 square for my prior variance for the temperature and its rate of change, and dependence of 0 for off diagonal terms. So Z is my prior probability of transiting between states. So it means I have a very, very high probability, so negligibly close to 1, if I'm in state 1 to stay in state 1, versus if I'm in state 2, going back in, if I'm in state 1, going in state 2. This is the probability if I'm in state 2, staying in state 2, if I'm in state 2, going back to state 1. So whenever I'm in state 1 or in state 2, I have a strong prior that tells me I remain in that state. So I need to define my two kinematics, okay? Now the transition model for my two regime. And here, the two regime, there's a specificity, needs to share the same hidden states. So the more complex model, one model as a zero speed model, the other model as a constant speed model. But both must have the same hidden state. So in that case, my vector of hidden state is the temperature and its rate of change. So my first model assumed that the speed is 0. So I'm going to force a 0 speed model by putting a 0 here in my transition model. So it means that at every time step, my knowledge of the speed would be 0 times the current knowledge of the speed. So it would always assume that my prior knowledge for the speed is 0. Okay, same here in that column. So having a 0 column here means I assume I have 0 speed for my first model. And for my second model, I'm going to assume that the speed is not constant, so that my transition matrix is like this. So the one that we've seen usually. So 1 delta t, so my xt, my temperature at time t, is temperature at time t minus 1 plus the speed at time t minus 1. Okay, and I have my Q1 and my Q here for model 2. And I need to have different matrices depending if I'm in model 1 and I'm staying in model 1 transiting to model 2, model 2 transiting to model 1, or model 2 and staying in model 2. So in that case, whenever I'm being or transiting from model 1, if I'm currently in model 1, so a 0 speed model, and I'm staying in a 0 speed model, or if I'm in a non-constant model, so I'm in a constant speed model, and I'm staying in constant speed model, or if I'm in a constant speed model and I'm transiting back to a 0 speed model, my covariance here can be treated as 0. Okay, we're going to see that in more detail in the next module Y. But in this case, we have no observation uncertainty, or we have no transition uncertainty. However, if we go from the 0 speed model to the constant speed model, we need to add some uncertainty here, okay, to account for the fact that if I change regime, I don't exactly know what's going to be the new speed in that new regime I'm going to transit to. So that's why when we transit from a 0 speed regime to a non-zero speed regime, I need to add some terms here for the speed term in order to account that in that transition, I'm going to have an uncertainty in what was my speed versus what is my new speed. Okay? So if we apply this model and we apply the Kalman filter equations, the switching Kalman filter equations, we're going to obtain this in terms of expected value in cyan and confidence interval in the red confidence region you can see here. You see that we need a couple of time steps in order to really capture the transition. But once we have transition, it's really clear that we're adding a change in the regime. Same here, we see that the underlying truth is the red line here. So we see that as it takes some time to realize, okay, my current 0 speed model is not explaining well what's going on. I need to have a regime switch. This is what we have here. And now that we switch the regime, we can infer what's my actual condition. So that was actually, this is my raw data. This is my temperature. This is my speed. Okay, the real speed is the dashed line. So we see that here at the point where we have an inflection, I go from a 0 speed to a non-zero speed. So the perfect thing would have been to jump right away. But since I have a lot of noise in my system, it takes me a couple of time steps to realize that my actual data is not correct. So in that case, I had a couple time lag. Then I realized, okay, I need a jump in my speed to actually explain what's going on with my data. And this is what we do here. And finally, we see that we need a couple of time steps to switch from a high probability of a zero speed regime to a high probability to a constant speed regime. And this is what the switching Kalman filter allows you to do, to put multiple dynamics in competition and estimate in real time as data come in, which model kinematics best explain what you're actually observing. Okay, this is what the switching Kalman filter will allow you to do. So there are some limitations that you must be aware of when using this in order not to be trapped into using it where it's not appropriate. So first is that the MLE parameter calibration is very sensitive to your initial value you're gonna provide, especially for sigma v, the prior standard deviation for the observation noise. So you have to be really careful at initializing the parameter in region that makes sense physically from an engineering point of view. Then if you just do an MLE for the parameters, it won't account for uncertainty in parameter estimate. That means you might need a lot of data, so many months of data, depending on the frequency of data acquisition, in order to have meaningful and representative parameter value estimates. Okay, in case where this is not true, you don't have enough data, or you want to really have a mission critical application where you need a real good estimation of your parameter, you need to use a Bayesian approach to do this. And if you want, go see our papers. We have plenty of papers where we describe as well Bayesian approach, either through sampling or analytical formulation. So it could be Laplace approximation to infer what could be the parameter value for in a Bayesian way rather than just a maximum likelihood. Another thing you have to be careful of is that you can have numerical error issues when performing the Kalman filter. So these are going to typically arise when the covariance for your posterior is going to be rapidly reduced in the measurement step. And that can happen, for example, when you use very accurate measurements. So measurement for which the standard deviation for the observation noise is going to be small. And if you use this after a long period with missing data. So whenever you have missing data, the confidence interval is going to tend to grow over time. And then if you have a very precise observation, it's going to make some instability in the covariance matrix, which may lead into some numerical issues. So negative covariance or stuff like this that will invalidate the result for the confidence region. And also it can happen when you have large differences between the variance of several states contributing to the same observation. So again, you have that ratio in your diagonal of your covariance matrix that might introduce some problem when you're trying to invert that matrix. That might lead to numerical errors. So the alternative and the solution to do this is that there are alternative paths to obtain the same thing as the Kalman filter, which are numerically more robust. Okay, the solution that leads to the same probabilistic estimate but in a more numerically robust way are either the UD filter or square root filter. So probabilistically, they are the same thing. They're going to be computationally a little more expensive, but they're going to be numerically a lot more robust. So if needed, these formulations are widely available in the literature or in already implemented code, either in MATLAB or in Python. Okay, what are the limitations associated with these state space model? Okay, first is that all the transition and observation model are assumed to be linear in the form AX plus B. Okay, the Kalman filter and smoother and the switching Kalman filter are only applicable for linear models. So if you want alternative approaches, you can use particle filter. So particle filter is a sampling based method that won't make any distributional assumption about the posterior PDF for your hidden state. It's going to be inferred through sampling over time. Okay, this is universal, except that it can be computationally really expensive. Okay, it has a lot of computational demand because you might need a lot of samples to efficiently explore your space. You have analytically approximate methods such as the unscented and extended Kalman filter, which will going to assume that your posterior is Gaussian and is going to approximate your Gaussian posterior using some approximation. So unscented is going to use some sample point estimation. Extended Kalman filter is going to linearize your nonlinear function. So all these methods are alternative that you can use if you have either nonlinear transition or observation models. Then another issue that consistently arrives in practice is that when you have non-uniform time step. So all these things we've seen assume that we always have time step for data collection that is uniform. If it's not the case, you have to be careful. You cannot directly use the same A, F, Q, and R matrices. These have to vary over time and now become time dependent. Okay, you have additional consideration you have to take care of if you have non-constant time steps. So be careful with this. So if we summarize what we've seen together, we have the transition model. This is the model that governs how do we transit from our prior knowledge of time t-1 to our current knowledge of time t. When I say knowledge, it's knowledge about the hidden state variable, okay? So this is governed by A, or transition matrix, and here we have W, which is the process error. That accounts for the fact that this transition model is an imperfect representation of the reality, okay? Where here Q is the covariance of that process error. I have my observation model, where yt equals f times xt plus vt, where vt is the observation error. V is a normal distribution, zero mean, covariance R, okay? Here, A is my model transition matrix, F is my model observation matrix. That controls which hidden states contribute, how the hidden state of time t-1 influence my hidden state of time t. F controls which of the hidden state in xt are actually observed, so contribute to my observation yt. I have my model error covariance matrix. I have my measurement error covariance matrix R. Okay, so we saw that we have three things we can do with the state space model formulation. Either filter. Filtering means estimating my current knowledge for the hidden state of time t, given all the data I've seen in the past. Okay, then we can do smoothing, meaning I want to use to estimate my best knowledge of time t, given all the data in the past as well as all the data in the future. And finally, forecasting, I want to use all the data in the past in order to forecast what is going to be the state and time steps in the future. So if we want to summarize everything we did with the Kalman filter, we can summarize this into that filter step, which take into account my prior knowledge of time t-1, my prior knowledge for covariance of time t-1, expected vector and covariance, my actual observation time t, and my model formulation, which is defined by A, F, Q, and R. Model transition matrix, model observation matrix, my covariance for the transition error, my covariance matrix for the observation errors. And this is gonna lead me to an expected vector and covariance, posterior expected vector, posterior covariance, describing my current posterior knowledge for my vector of hidden state xt, given all the data from y1 up to time t, okay? It's gonna also provide me a joint log likelihood that present how likely my parameter value were into predicting the data as I was receiving it. So we can break down that filtering into the prediction step. This is simply propagating forward my current knowledge into my transition model, and a measurement step. This is the place where we use the Gaussian conditional equation in order to obtain these posterior conditional mean vector and covariance matrix. And at the end, remember, these four matrices may contain several unknown parameters, okay, that we need to learn from data. How do we do this? By using, for instance, a maximization approach, where we're going to use an MLE, where we're going to find the optimal parameter value that maximizes the sum of the marginal likelihood, or the sum here of the log likelihood at each time t, where the marginal probability of each data is given by this quantity, which is jointly normal. Okay, so in the next module that's going to follow, we're going to see how can we build these linear model structure to very easily adapt to a vast array of possible reality, and how can we use these into ready-made code in order to analyze large volumes of time series data. We're going to look here at the OpenBDLM code. We're going to all see this in the second part of the class where we're going to see these linear model structures.